Hello everyone, welcome to my IGP Summit presentation. My name is Mingyang and I'm going to present on my experiences in studying abroad to China, specifically in Shantou University of Guangdong Province, because I study abroad in Shantou University. But first, I will talk about my research experiences which I began at NAU. Then I will talk about my cultural immersion and linguistic experiences at Shantou University. Lastly, I would lightly touch on my evacuation experiences and my subsequent short study at Cetis University of Mexico. My research project is a novel field in nanophysics. The field is sometimes called microswimmer self-assemblies or colloidal motors development. It is in the nano to micro regime and focuses on investigating the mechanisms of how these small particles move. I myself have been studying the mechanisms of how these individual particles move, as well as creating particles in group motion in order to make them move together. Without further ado, let's begin. In the past, I was involved in projects that study how particles in a liquid solution interact with the surfaces upon which they move. I've also studied on how the shape of particles dictate their motions when activated with a light source, as well as how the concentration of particles determine their expansion and contraction. These studies of individual particles are preparatory studies to create self-assemblies of bulk movements. The reason scientists are interested in making them self-assemble is because we need to develop machinery that can move in a uniform direction to be able to control materials at this small scale. For example, scientists are now developing microswimmers for medical applications, such as drug cargo delivery. What scientists envision with these projects is what scientists envision to accomplish with these projects is to have these microswimmers hold a drug and deliver it to a specific organelles, as shown in this picture. You might say that a single particle could potentially do that, so why spend the efforts to make bulk movements? Well, there are maybe several reasons to that question. A single particle may be able to deliver a drug cargo, but remember that these are extremely small particles. A small drug cargo might not be enough for the dosage of a patient. We don't want to expend energies just to deliver a single drug cargo to a cell. Particles interact with each other when they move. If we can find ways to exploit their inertia, we could save more energy in more efficiently delivering drug cargoes. There are also other potential applications for self-assemblies. Suppose we detected cancer cells in some parts of our body that haven't diffused through bloodstreams. We could send these microswimmers to the cancer cells and destroy them by exciting the microswimmers when they reach the cancer cells. Currently, we can use UV light to excite the microswimmers, which are harmful to our bodies. But scientists have also developed microswimmers that can be activated through blue light, but in a less intense manner. If we can develop microswimmers with particular shapes and materials that react actively under light with a benign wavelength, then we could be one step toward accomplishing this goal of destroying cancer cells. There are a few wavelengths that can both penetrate our skin and activate the microswimmers. However, this field of studying microswimmers have many degrees of freedom. On this slide, we see a snapshot of my poster. What I want to accomplish with this presentation is to introduce 3 ways that scientists have used in studying microswimmers and developing self-assemblies. The reason I want to do this is because understanding some of the basic mechanisms of self-assemblies can give us a vision of how future works in self-assemblies would develop. It gives us a range of possibilities of what self-assemblies can or cannot do. On the last slide, I mentioned that microswimmers have many degrees of freedom. This means that there are different ways of activating the microswimmers, as well as many different ways to control the motions of microswimmers. Combining them in different ways allow us to design the ideal machinery for the required task and situation. For this short presentation, I have only chosen 3 mechanisms that scientists used in designing microswimmer machineries. My hope is that you can gain some background of this area after listening to this short presentation of mine. The three mechanisms that will be introduced are UV activation, magnetic induction, and geometric design. Here is a snapshot of figures from a paper that I co-authored. It represents a typical microswimmer in a fluid environment. When we study them, they are diffused in solutions of water and hydrogen peroxide. Hydrogen peroxide is a poisonous solution, but it is required to activate the particles. We were in the developing stage of designing microswimmers, so we focused on understanding how the particles move before designing their applications. Once we understand how they move fundamentally, we can replace hydrogen peroxide with other harmless sources. In all the examples that I will introduce in this presentation, they move in a fluid environment. So I will first introduce to you how microswimmers move in a fluid environment upon a surface. When an incoming light source activates the microswimmer, there are two fluid motion around the particle that serves to propel or slow down the particle. There is the phoretic flow over the head of the microswimmer, which makes the particle go tail first. And there is the osmotic flow, which expands outward from the point where the particle is closest to the surface. If a particle is to move in a bloodstream, they would interact with the walls of the blood vessels. So that's the reason why we are interested in learning how particles interact with the surfaces. The first method that propels microswimmers is activated by ultraviolet light. These particles would be prepared in liquid solutions that are mixed with water and hydrogen peroxide. They would sit in the solution and have some Brownian motion, which are random fluctuations. When UV light shines on them, energy stored in the light would transfer to electrons in the titanium dioxide. The excited electrons would be attracted to the gold side, or AU. Additionally, energies from light catalyzes chemical reactions involving hydrogen peroxide, which result in a polarized solution that is charged. When a multitude of electrons swim from the titanium dioxide side to the gold side, the electrons also attract the positively charged fluid around the microswimmers from the titanium dioxide side to the gold side. From last slide, we see that when fluid is transferred around the particles, the fluid propels the particles. Similarly, the reactions in this slide, particles are propelled because of the fluid motion around particles. The second method that I like to introduce is magnetic induction. The picture is taken from a published paper with an experiment in the cell. This project demonstrated that it is possible to maneuver particles along a desired direction in a cellular condition. Moreover, there is the advantage of not having to worry about the toxicity of hydrogen peroxide. The particle is designed to be helical in shape, and magnetic fields are present around the particle. Depending on where the particle needs to be directed, magnetic fields are altered. The last method to alter particle motions, which I prepared for this presentation, is morphological design. It has been shown that particles respond to activation sources in a shape-dependent way. On the top, we have two shuriken-shaped flat disks. They have different spiral directions, and scientists have shown that they rotate in different directions if the spiral is altered. On the bottom, we have two different depositions in which the gold is either positioned on the tail or on the side of the microswimmer. Changing the deposition of gold would change the direction of motion of microswimmers when activated by UV light. This is all I prepared for my research experiences presentation. Microswimmers have a lot of potentials to be realized as machinery for us to navigate the extremely small environment. There are many energies that, there are many degrees of freedom that we can use to control them. Internally, we can control their shapes. Externally, we can control their excitation sources. We could also turn external conditions to internal conditions. For example, scientists can create microswimmers with magnetic properties. In turn, we could also alter their shapes. So I think microswimmer have strong potentials as feasible tools for us in the future. Next, I'd like to talk about my experiences in Shantou. Last time we met through Zoom, some of you asked me what it is like to live in Shantou. I'm going to spend a little time to show you the dorm. So here are two panoramas that I took. There is a small living room and a short aisle that leads to two rooms, each with two beds. There is a private bathroom and toilet. I will say it is a comfortable setting for studying abroad. The building has 6 stories. On each story is 2 apartment rooms. It is not very big for 4 persons, but of course the point of studying abroad is not to spend time in your rooms all the time. There are many things you can do while studying in STU, which I will show you later in this presentation. The top right is a picture of what you would see when you step outside of your dorm. There is a small balcony and it faces a mountain that surrounds the north side of STU. On the top left corner is a picture of the STU library. I have cleaner pictures later in this presentation. I just want to show you a good looking sunset there. On the bottom left is a food street just by the STU. The gate that you see in the picture leads to Shantou University. It has many delicious and inexpensive cuisines. I definitely recommend you to try it out if you have a chance. It's part of the typical experience of a student in a Chinese university. Here are some photos. Um, sorry, I missed my transcript. Here are some photos of the mountain by STU. So occasionally we would spend time and hike with each other, with local students as well as students studying abroad. As you can see from the top left corner, there are Korean students, Lithuanian students, Indian students, um, Irish students, um, as well as Spanish students. And there are good scenery on the mountains and it's a safe hike. And on the bottom left corner is a picture of the um, STU campus when you see from a bird's eye view. And here are some photos of the STU library. It has an interesting infrastructure, I would say. I'm not sure if it is the most effective design because as you can see from the two photos to the left, a lot of space is left open in midair. At the NEU library, there are certain places where you can look down from the second story with a cuboid of space, and comparatively the space is small, but at STU, I was just surprised how there are space left out in the open. Um, um, I think they are more for architectural design purposes, more than to be for efficiency. As you probably know, I was fluent in Chinese by the time I studied abroad in China. I wanted to get the social and academic experience of what it is like to study in a Chinese university. I didn't take any classes teaching Chinese. Instead, I took some STEM major classes. What I did for my linguistic experience is that I went to this outdoor camp that provides elementary and middle school students opportunities to better interact um, with each other and just to have some fun. Basically, I was their mentor for 3 days. They tied rafts and learned how to buy groceries and how to cook, make some barbecues. Some of the other international students were there to teach English just for a day. It was a lot of fun, but also very exhausting. Um, I had to contact parents when they have concerns of their children, but I think it was a rewarding experience in seeing how Chinese students at my age work to earn money. With the COVID pandemic, I couldn't continue with my STU experience. I evacuated out of China by February the 5th, and I was put to study abroad in Setis University as an alternative studying abroad experience. So here are some photos of Mexicali. It is an area that is typically hot around the year, and um, it is very rare um, for there to be rain, and I guess I was lucky. Um, Originally, the plan was to have me complete a rocket project with an engineering team at Satis, but I couldn't finish it because Mexico also caught up with COVID. 3 weeks I traveled there. So, but it was fun meeting new people. Um, so that concludes my whole presentation. I hope you have enjoyed this presentation, that you may have found some information to be interesting or useful.